For today's airlines, Western Europe is not a large area, and the flights they make within it are of short duration. Therefore, it should be possible within such an area to arrange air traffic control clearances and instructions in such a way that any aircraft will fly its most economic profile, without the changes to route and altitude necessary in the present system, which are so disruptive to the smooth flow of air traffic. If Brussels is taken as the centre of our study area, a number of major airports lie within half an hour's flying time, like Amsterdam, Paris, London, Frankfurt, and most of Europe's major cities are only 1.5 hours from Brussels. For these flights, and more especially the shorter ones, any increase in the time en route or distance flown, either through holding or through vectoring, will have an increasingly negative effect on flight economy. As the annual growth rate of air transport remains high, it is to be expected that the density and complexity of air traffic will continue to increase appreciably over the next 10 years. This in turn will increase runway utilization at existing airports, with the result that even a slight increase in traffic will lead to a disproportional increase in delays. Therefore, due to the geographical size of Europe, the system handling air traffic within 1 or 2 hours of flight of the selected central point should consider each flight as a complete entity and not as a succession of individual phases. This means that the management of flights should be arranged accordingly, and clearly implies a need for a tool to predict and organize the flow of air traffic. When compared to aircraft automation, which has now reached such a level that it is conceivable to fly fully automatically from departure to destination with just a monitoring crew on board, no system has been introduced into ATC for the automatic generation of directives to assist the air traffic controllers in guiding aircraft. The management of air traffic and guidance of aircraft in and around major terminal areas will be the next evolutionary step in air traffic control. This requires the introduction of a knowledge-based control system which will actually assist the air traffic controller in the decision-making process. Such a system will affect nearly all fields of ATC, from the overall air traffic management at the planning level to the selection of conflict solutions at the executive level. One state-of-the-art approach is the Zone of Convergence, or ZOC concept, developed by the Engineering Directorate of the EUROCONTROL Agency in Brussels. This tackles the problem of efficient online management of a stream of aircraft inbound to one or more major airports within a TMA by advising the approach controllers on how to manage the traffic flow for minimum cost to the airlines and the maximum efficiency for ATC. Therefore, optimizing the available capacity while at the same time ensuring normal safety standards. Several research institutions have reported on their activities in this field, and although the projects are often adapted to specific local situations, their approaches are generally similar and consist of the following modules. A sequencer scheduler module. This establishes a target landing sequence and its associated landing times using one or more optimization criteria. A guidance and control module. This generates the ATC advisories to achieve the planned sequence based on observed radar tracks. And a man-machine interface module to facilitate an ergonomic controller dialogue, which should be compatible with the existing controller working position and the ATC data processing system. But before entering into details, let us point out that the present ATC system is fail-safe, in that the stack constitutes the regulating reservoir, and in the case of traffic overload, the possibility of keeping departure aircraft on the ground remains. ZOC management avoids the systematic use of holding aircraft. It calculates the time of arrival and determines the speeds that aircraft must arrive at the entry points in order to achieve a continuous and efficient flow of traffic. This operation depends almost entirely on the traffic situation and aircraft performance. The ZOC management, therefore, is more efficient than the present ATC procedures, eliminating the reliable but costly holding of aircraft. The latest development of the ZOC initial concept covers a large volume of airspace surrounding a major and secondary airports, extending out to 100 or even 300 nautical miles, therefore enabling a real integration of the traffic flow into cruise, descent, approach, landing and possibly climb phases. At this point, it may be appropriate to define what we mean by preferential and actual trajectories as used in the ZOC system. For each aircraft entering the area, irrespective of the direction of flight, there is an optimum flight profile which best meets an operator's requirements, essentially a combination of route, altitude and speed. The optimization of these criteria for economy and flow capacity is what we call the preferential trajectory. If there were only one aircraft in the area, it would obviously fly the preferential trajectory. In reality, this will probably conflict with the flight profiles of other aircraft already in the management guidance area, so the aircraft will have to depart from its preferential trajectory and fly what we call an actual trajectory. In both the present fixed routes network as well as any future free route system, the routes are determined and assigned according to local considerations, such as restricted areas, availability of navigational aids, traffic loading and so on. Consequently, they are most unlikely to coincide with the preferential profile of an operator and can actually be dismissed from the criteria to be considered. The altitude and speed of the preferential trajectories are usually presented as a sequence of phases, each with a constant indicated airspeed or Mach number and total temperature, which are as close to the theoretical optimum as possible. In the present operational system, aircraft are often allowed to follow their preferential profile until a point where conflict becomes likely, usually as far as the stack for most arriving aircraft. The subsequent holding results in a fuel consumption and time penalty, which increases very rapidly when traffic saturation is approached. In contrast, the management guidance system of ZOC looks approximately 1 hour ahead, depending on the size of the zone concerned, and assigns a set of trajectories to achieve the overall traffic flow and satisfy the individual aircraft requirements, yet are still flexible enough to permit air traffic control to function. To evaluate the human presence in the control loop, a full-scale air traffic control simulation of this new ZOC concept was conducted in June 1989 at the EUROCONTROL Experimental Center in Bretigny-sur-Orge, France. The proposed display of information and controller procedures were assessed and proved to be compatible with the present air traffic control operations in both en route and TMA sectors, even under heavy traffic conditions. Flight simulators at Sabina, British Airways, KLM and Aeroformation, flown by airline crews and controlled by local ATC personnel, were used to test the ZOC system with extremely favourable results. Now let us examine the various processing steps in the ZOC system. Online management of air traffic relies heavily on the predicted flight profiles of the individual aircraft, even when the routes to be followed and the operating procedures have been agreed upon by the aircraft operator and ATC in advance. The validity of the predicted profile is nevertheless strongly affected by numerous random disturbances, such as uncertain meteorological conditions, conflict resolution which force an aircraft to leave their planned route or vertical profile, errors resulting from radio communication difficulties, human errors in the air and on the ground. Because ZOC is used in an operational environment and therefore subject to many disturbances, this system incorporates a dynamic sequencing and scheduling mechanism, where the landing sequence is constantly checked against the actual traffic development. This approach offers complete freedom of action to the controller. However, it enormously complicates the provision of useful computer-based assistance, especially when heavy workload requires computer inputs to be kept to a minimum. It is in this area that most of the research has been concentrated. The principal steps involved in the process are shown in this picture. The system is triggered every time new radar data is generated. If the data on new aircraft entering the area becomes available, an estimate of its preferred flight profile is calculated. That is the profile the aircraft would follow if it were the only one in the area. A landing sequence is then proposed based on the preferred flight profiles of all the aircraft. A landing time is calculated for each flight depending upon its position in the landing sequence, the estimated landing time of the preceding aircraft, and the minimum separation to be maintained on final approach. The four-dimensional start and end positions are then defined for each flight, after which an attempt is made to find a matching flight profile from the aircraft's present position until touchdown, within the limitations of the aircraft's performance and ATC constraints. On completion of this initial step, the future flight paths can be calculated and runway utilization and potential en route conflicts can be assessed. If the result of this evaluation is acceptable, ATC advisories are generated by the computer and displayed to the controller, or the landing sequence is simply updated. In this sequence of steps, there are three main modules. The central module is the Regional Organization of Scheduling and Sequencing, or ROSAS. This takes into consideration routes, ATC and company procedures, meteorological data, conflicts, etc., to produce a landing sequence. The control of inbound trajectories for individual aircraft, Cynthia in ZOC terminology, monitors the radar positions and adjusts the actual trajectories of inbound aircraft by constantly updating the guidance and control advisories. Finally, the man-machine interface. This generates and arranges the display of ATC advisories. The ZOC system has been designed so as not to require any additional displays at the controller working position. The ATC advisories generated by Cynthia may contain a descent time, an airspeed, an optimum turning point and subsequent heading, and can be displayed without causing inconvenience using an additional line of the aircraft's identification label on the controller's screen, which avoids the need to scan other displays. Once the scheduling and sequencing component of ROSAS has organized the traffic flow characteristics of arriving aircraft, the actual trajectories are adapted to a new plan by the guidance and control component of Cynthia, and the relevant advisories are dispatched to the control positions concerned for implementation. As you can see in this example showing an inbound aircraft, a third line is added to the radar label containing the ATC advisories produced by Cynthia. The first line of the label gives the call sign of the aircraft, Sabina 704, its weight category, medium, as wake turbulence separation must be taken into account, and the current position in the landing sequence, in this case number 4. The second line shows the Mode C flight level of the aircraft, 30, and the radar ground speed, 220 knots. The ATC advisory in the third line indicates to the controller that the optimum point for turn onto base leg, a heading of 120, is 7.5 nautical miles before the Bravo Uniform November beacon. The advisories turn red or flash on a monochrome display so as to alert the controller that the suggested action should now be taken. The structure of the generated messages is compatible with automatic digital ground-air data communications as planned for the future Mode S data link. The ROSAS and Cynthia components of the ZOC system have been designed around the principles of distributed processing. That is to say, it can be introduced at an operational centre using a separate small processor, thus avoiding the difficulties of integration into a complex ATC system based on a mainframe computer. Brussels National Airport. The Sabina Flight Simulator Department. To validate the Cynthia algorithms, a portable simulation system is used to conduct large-scale exercises using flight simulators and a synthetic pilot position, which can generate up to 10 more additional aircraft. As only a flight simulator operated by an airline crew can approach the real performance of an aircraft, the results of the proposed ground-based four-dimensional guidance of flights, even in extreme meteorological conditions, were considered valid and capable of maintaining the arrival time of aircraft to within 10 seconds of a prediction made up to 2 hours previously. A further evaluation is being carried out here, using simultaneously a DC-10 and a Boeing 737 flight simulator. Airline crews from Sabina and ATC personnel from Amsterdam and Brussels participate in the simulation after only a short pre-flight briefing on the ZOC procedures. It should be noted that no particular training on the ZOC system is necessary. Both the air traffic controllers and the pilots are taking part in the exercise for the first time. The simulation is now underway, and 2 exercises will be run, each composed of a series of 2 flights. All the flights are inbound to Brussels, the DC-10 coming from the north via Machel, and the 737 from the south via Sèvres. The 2 flight simulators are integrated into a traffic flow of 5 other aircraft generated by the synthetic pilot position. At the initial inbound points, the DC-10 and the 737 are in level flight at an altitude of 10,000 feet. From there on, both proceed towards Kirky, following the Brno standard terminal arrival procedure to land on runway 25 left. The use of the autopilot, or the flight management system, is left to the pilot. None of the aircraft are equipped with 4-dimensional navigation equipment, and the time of arrival predicted at the entry points, either Machel or Sèvres, will not be transmitted to the pilots by the controller. The arrival time at Machel and Sèvres are selected so that without controller intervention, the aircraft would be in conflict over Kirky. The problem for the controller is to solve the conflict at the converging point by modifying the standard inbound flight path in the horizontal or vertical plane, or both, and then implement the computer advisories appearing in the relevant radar labels. Each flight lasts 15 to 20 minutes, which corresponds to a track length of 60 to 80 nautical miles. After 2 flights, a mid-session debriefing permits constructive exchange of comments between the pilots and controllers and allows the ZOC team to eventually improve on the procedure details. At the final debriefing, the professional pilots who flew the flight simulators expressed their satisfaction with the ZOC procedures used in the exercise. The controllers recognized the need for assistance from an advanced computer-driven tool for the regulation of arrival flights at busy airports. The results of these simulations show that the advisories generated by ZOC are fully compatible with cockpit, ATC and company operating procedures. The ZOC concept fulfills its objects by offering the controller not only a real reduction in workload, but also provides the indications necessary to achieve the best sequencing and consequently the trajectory closest to that required by the company.